Hello and welcome. So far, we have mainly talked about global averages, global trends. Now we're going to focus in on regional phenomenon, stuff that we're actually dealing with here in Georgia. So let's get started. I will share my screen, start the PowerPoint, and here we go. So climate phenomena and their relevance for future regional climate change with a focus on Georgia. Now, Georgia, even though we are on land, a lot of our climate and a lot of our weather has to do with natural cycles in the ocean. And warmer or colder than average ocean temperatures in one part of the world can influence weather around the globe. So I'm not just talking about changes in the Atlantic Ocean affecting our weather and climate. I'm talking about changes in all oceans. Even the Pacific Ocean on the other side of the world can indeed affect our weather and climate. So you may have heard of the infamous El Nino Southern Oscillation, or ENSO, or El Nino. And we'll talk about that, how that has influences on our weather and climate. But that's actually not the most important one. The most important one, which you may not have heard of, at least for Georgia, is AMO, or the Atlantic Multidecadal Oscillation. Now, this is a natural cycle in the Atlantic Ocean that impacts our weather and climate, has nothing to do with climate change. It's the natural variability of the sea surface temperature of the North Atlantic Ocean over several decades, and it's linked to the speed of the oceanic thermohaline circulation. Thermo meaning temperature, haline meaning salinity, right? So the way that the density of the water due to the temperature and salinity is moving around the oceans, basically the global conveyor belt in the ocean. Right? Now, if you look at this graph, it is showing observations going back over 100 years, all the way back to 1880. And you can see that there's this natural variation where it goes from positive or a warm phase in the North Atlantic to a negative or a cool phase in the North Atlantic about every 70 years. Right? So every 70 years or so, the North Atlantic gets naturally warmer. 70 years later, it gets naturally cooler. And this is just a natural cycle. Again, has nothing to do with climate change. Right? The oscillation causes periodic warming in the North Atlantic and cooling of the South Atlantic over a 70-year cycle, and then it reverses. So after the end of that cycle, it will be cool in the North Atlantic and warm in the South Atlantic, as you can see in this image. Now, warmer temperatures in the North Atlantic, or what we call a positive phase of AMO, can lead to a lot of things. First is increased hurricane activity in the North Atlantic, which makes sense, right? Because hurricanes are fueled by warm water that evaporates into the atmosphere. That warm water provides energy for the hurricane. So the warmer the water of the North Atlantic, the more hurricane activity we're going to have. It can also cause drier conditions in the western part of the US where it's already dry. When you amplify the water cycle, not only are you causing wet places to get wetter, you're causing dry places to get drier. So dry conditions in North America, this actually contributed to the 1930s Dust Bowl. Just like you have increased hurricane activity around us and around the equator, you'll get wetter summers in Northern Europe because that warm water is bringing more warm, moist air to Northern Europe. You'll get lots of other things too: heavy rainfall in the African Sahel, droughts in Northeast Brazil, less sea ice in the Arctic, wetter Indian monsoons, so on and so on and so on. So notice how the temperature of the ocean can cause a lot of different weather impacts around the world, not just right around the coast of the Atlantic. Now, multiple lines of evidence from paleo reconstructions and model simulations indicate that AMO is unlikely to change its behavior in the future as the mean climate changes. This means that 70-year cycle of positive phase, cool phase, or positive phase, which is warm, negative phase, which is cool, back and forth every 70 years, we don't expect that cycle to change. Now, this doesn't mean that we don't think it's going to be overprinted on top of climate change, right? Overall, the temperature of the ocean is going to warm, we expect, and it is already warming. We're just still going to have this natural cycle on top of that. So this brings up a really important question on how we interpret observations and analyze observations. Because notice, because of this natural cycle, when we look at this, 140-year time series, we can see that natural cycle and we can pick out the cycle from the overall trends. However, let's say, we were to only look at this graph starting in 1980. right? If we were to only look at the graph starting in 1980, we would only see a drastic warming in the Atlantic Ocean. So how would you be able to tease this natural trend apart from global warming? So if we only see that increase in temperature, how do we know what's causing it? Humans, or is it a natural cycle? There's lots of ways to go about teasing apart natural cycles from global trends. And I would say the best way is to look at multiple locations on Earth, right? Notice that this Atlantic multidecadal oscillation mainly occurs in the North Atlantic. So if we were to look at time series from all around the world, yes, every single location is going to be influenced by its natural cycles and whatever ocean basin it's in. But if we see that every single spot on Earth, or almost all spots on Earth, have an increase in temperature imprinted on top of this natural oscillation, then we can start to say, oh, we're not just seeing it in one ocean due to one natural oscillation. We're seeing it everywhere. This has to be a global phenomenon. It has to be global warming. Another way we can start teasing this apart is by comparing the rates of warming, right? So in this time series, we have at least 2 periods of negative cool phase recorded, and each of those goes into a positive warm phase. So we can look at the rate of warming between the negatives and the following positives and figure out, well, what's the natural rate without global warming? What's that natural rate? And is the rate we're seeing today faster? And based just on this time series, yeah, it looks faster. It looks like the positive warm phase that we're seeing today is more extreme than the previous positive warm phase. Now, this is a data set of 2, right, which we should not make interpretations from. You need much more information to make a confident conclusion. But again, if we were to do this all over the world and see, oh, yes, everywhere in the world, even when we have these natural oscillations, it looks like the most recent warm phase is more extreme, then that can tell us, oh, yeah, it's probably global warming, not just these natural phases.